All right, I hope everyone had a good weekend. Are there any questions over anything? Homework or anything? We're good? All right. All right, so just a quick summary of what we did last time. We were doing the derivative of a function, which we were able to recover the slope of a tangent line to a curve. And we also were able to find the equation of the tangent line to a curve. But we had to use this thing, this limit to do it, right? And we saw in class that that was somewhat tedious, that the algebra could get a little messy. And we're going to move kind of away from this. We're still going to be talking about the derivative, but it turns out that there's some shortcuts that we can use, formulas really, that will allow us to still do the same exact thing we were doing here, but without having to use the limit. And that's a very, very good thing, all right? So we're going to do that, and we want to look at the derivative as creating a new function. I'm going to explain that. That's where I'm going to start. So if you have your notes from last time, I would like for somebody to give me one of the examples that I gave you where I wanted you to find the slope of the tangent line at several different points. So any of those examples. Give me an example of the function I gave you. F of x is what? 5x squared plus 3, that was it? Okay, so that was one of the first ones that we did. Not the first one, but I think that was the second one we did. Okay, so if you look back in your work, I tried to convince you that what we could do to do this was, instead of finding it at each point, to do it at A, and then calculate, do the limit, and then at the end our answer would have something with A in it. And we did that, right? If you look back in your work, we did limit, h goes to 0, and then a bunch of stuff. And at the very end, what did we get? What did we get? 10a, right? 10a. All right, so the idea here was that we have some function. This is it right here. It's a parabola, it opens up. And if we go to some point A, let's call this A, that the slope of the tangent line will be 10 times that number A, right? And so you could plug in any value you want for A, and then we'd be able to get the slope of this tangent line. Well, since the derivative of the function depends on A, we can look at the derivative of this function as being a brand new function. Let me phrase it this way. What if instead of saying, here, go to A, I said, well, let's just call that x, because it is an x value, isn't it? Then I would replace this with x. And then in the formula, the only thing that would change would be that we would get 10x, right? Instead of 10a. So you start with this function, f of x, right? There it is. You do this thing called the derivative. And you get this new function. Let me write it this way. F prime of x. And it now is a brand new function, 10x. Understand? All I'm doing right now is I'm replacing the a with x. Now the reason we didn't do that way before is because the book uses a. So I wanted to stick with what the book uses. But now what we want to do is realize we start with a function. Whatever it is, it's a function of x. We take a derivative and we get a brand new function. This function is now also a function of x. But they're different, right? They're different. But there's a relationship between them. This one gives you the slope of the tangent line at x of this curve. You with me? Okay. Now, we are going to start 10.5. And I think you're really going to be happy when you see this. And those of you, I know some of you in here have already seen this. And you know how nice it is. So 10.5, or what we call our basic differentiation rules. Now that word differentiation just means these are the rules that we have, our basic rules for taking derivatives. The actual process of taking the derivative of a function is called differentiation. All right? So these are the basic rules, and you want to memorize these rules. And I'm wondering if I should go in the order of the book. Well, I guess I will. So let's get some notation out of the way first. Notation. If y is some function of x. So we have some function right here, right? This is some function of x. And when we graph it, we usually use x as the x-axis, right? And we usually say that y, this is the y-axis, right? So y is a function of x. So if we start out with a function of x right here, then f prime of x means take the derivative of it, right? That's the notation that we used from last class. Y'all remember that little prime mark? Okay, that means take the derivative. But that's also the same as this notation, dy dx. Okay, so if you see dy dx, it means exactly the same thing as this. So we have two different notations for the same exact thing. And there's actually a historic reason why this is the way it is. It's because there were two people who came up with calculus at the same time. There was Isaac Newton, and there was another guy, Leibniz. And they actually developed calculus independent of one another on different parts of the world at the same time. And then when they wrote their books about calculus, and then they got together and said, oh my gosh, we were thinking about the same thing. But they used different notations. Since they were creating the mathematics, they actually had their own notation for the same processes. So that's why there's two different notations. This is Leibniz's notation, this is Newton's notation. Okay? This is the same as, there's another notation, y prime. So look, you see how this says f prime of x? Well, if f of x is replaced with y, then y prime means the same thing. So all three of those mean take the derivative, okay? And there's another one. D dx of f. Well, f of x, that's fine. I know this all looks really weird, but first time seeing it. So what this is saying is I want to take the derivative. X is my variable. And what am I taking the derivative of? Well, the function, okay? The function, f of x. All right, so these are all the same, okay? In mathematics, we actually write this abbreviation, and what it stands for is the following are equivalent. In other words, all these are exactly the same thing. They mean exactly the same thing. All right? You don't need to know that. I'm just telling you. Okay, so we now have some notation. If you see any of these symbols used, that means that you're trying to take the derivative of something. All right? Now the rules. The first rule is the constant rule. I'll label it rule 1. The constant rule. And here's how I'm going to write it. If f of x is c, where c is any constant. What do I mean by constant? What do I mean by that? It's just a number, right? So like if our function is f of x equals 5, or f of x equals 10, or f of x equals negative 3, whatever it is, if it's a constant, then f prime of x is, so we would have to do the limit, wouldn't we, to figure out what this is? But I'm giving you a shortcut right now. I'm going to tell you what the derivative is without us doing any limits. If your function is a constant, what do you think the derivative would be? So think about this. What does a constant function look like? If I ask you to graph it, what does it look like? Flat line, horizontal, right? And if I ask you to look at any point on this curve, or on this line, and tell me the slope of the tangent line, what's the slope of the tangent line going to be? 0. Because horizontal lines have a slope of 0, don't they? So that's the answer. The derivative of any constant is 0. With me? Got it? Okay, that's the first rule. Second rule. The identity. If f of x equals x, then f prime of x equals, let's think about this one. Do you all know what the function f of x equals x looks like? What type of graph is this? It's a line, right? What's the slope of this line? 1, right? Because the number in front is a 1. So look, that's not, the first rule we were talking about a function that was flat. The second rule has to do with the line that has a perfect diagonal, perfect slope of 1, right? So if I pick any point on this line and ask you for the slope should be what? The same as the slope of the line, right? Which should be 1? Yes? That's the answer. So what is the derivative of x? What's the derivative of x? 1. What's the derivative of 4? 0. Okay? This is what we know so far without doing any limits. I'm telling you this. You're kind of taking it on faith, all right? In a Calculus 1 class, a true Calculus 1 class, we would prove each of these. We would actually do the limits and show that you get 0 and show that you get 1. But here I'm just going to, here they are, all right? All right, next one. And this one is just super important, all right, this one. You still need to know those, but this one is used a lot. This is the power rule. The power rule. If f of x equals x raised to any power. Okay, so this was x to the first power, wasn't it? But what if we have like x squared or x cubed or some weird power of x, right? What's the derivative? Well, I'm here to tell you what it is. It is equal to n times x raised to the n minus 1. All right, so let me explain what's happening here. Because instead of memorizing the formula, you can think about what just happened. We have x raised to a power n, right? What happens is when you take the derivative, the n comes out in front. See the n out here? And then it's x raised to, not to n, but 1 less than n. So what's happening is the power drops out front, and then the power comes down by 1. Understand? I'm going to give you examples of all of these, but you kind of see how that pattern works. N comes out, subtract 1 from n. All right, that works for any power of x without doing any limit. It's awesome. All right, next one. The constant multiple rule. Okay, so be careful here. We have up here our first rule was the constant rule, right? And we said the derivative of a constant was 0, right? This is the constant multiple rule. It's different. So let me show you how this works. Let's say that you have some constant times some function of x. So here, wasn't it just the constant by itself? Right? Just the function was just a constant. But this is saying, let's say you have some number sitting in front of a function, and you want to take the derivative, okay? You okay with that? I'm going to give you an example, but then the derivative, I'm going to use different notation here, of this constant times the function is equal to the constant times the derivative of the function. Okay, now that's definitely going to confuse you, all that notation there. Doesn't that look a little confusing? Yes? So let me show you an example of this right now, because I think once I show you an example, you'll agree that it's not as bad as it looks. Okay? So I'm going to get rid of this rule up here, and I'll do an example of Rule 4. As an example, let's take the function f of x equals 5x squared. Okay. Let's say I wanted to take the derivative of this, all right? I wanted to do the derivative. Do you see that you have a constant being multiplied by a function? Yes? It's not a constant by itself. It's a constant times a function. This rule says that if you want to take the derivative of a constant times a function, that what you do is you just don't touch the constant. Leave the constant alone and take the derivative of the function. So if I want to know what the derivative of this is, what I'm going to do is I'm going to bring the 5 down. I'm not going to touch it. I like to say that 5 is just going to come along for the ride. Okay? It's just going to come with us, not touching it. There it is. Now, x squared, what is the derivative of x squared? So now you have to go back to this rule right here. Isn't that x to a power? Yes? So what should happen to that power? It should come down out front. Now I'm going to put it right here, 2. And then I'm going to rewrite x in x to what power? 1 power, right? The first power. Because I subtract 1 from this power. And what is this? 5 times 2, right? 10. And then x to the first power is just x. So we get 10x, don't we? And that's it. Do you understand how this constant multiple works? Now, again, had this function just been 5, what would the derivative be? 0. Okay? But because it's attached to a function, because it's multiplied to a function, the 5 comes along for the ride. That's the only time it happens. It has to be attached to something. Okay, 5th rule. If you have some function of x plus or minus some other function of x. So let's say you have 2 functions with plus or minus between them. Then the derivative of that. Okay, so you have 2 things being added or subtracted. If you want to take the derivative of these things being added or subtracted, then that is equal to the derivative of the f plus or minus the derivative of the g. This rule is very important. It's telling us that as long as you have addition and subtraction between things, you may take the derivative of each one of them individually. Okay, you see, you're doing the f by itself, then the g by itself. You're doing the derivative of each one. And I'll show you an example of that. So I think somebody give me another example we did last class that had where I gave you a function that had a couple of pieces in it. What do you got? How about the one I asked you to work on by yourselves? Remember that one? It was negative 3x squared plus 2x minus 7. Okay, do you remember the amount of work that required? I walked around, you worked together, you tried to, and there were some issues with this, right? Okay, we should be able to do this problem now without doing any limits. So the first thing I'm going to notice is that the function I'm looking at has pluses and minuses, right? And this rule right here says that if you have pluses and minuses, you are allowed to do them individually. So in other words, I can kind of like break up this into like 3 different pieces. And I can take the derivative of each of those pieces. Okay? So let's look at that first piece, negative 3x squared. This negative 3 in front is a constant, right? But it's being multiplied times x squared. So the negative 3 is going to, the derivative is going to be 0, or is it going to come along for the ride? It's going to come along for the ride. So I'm ready to write the derivative out here. F prime of x is equal to, so the negative 3 comes for the ride. and then I say times. Now, what is the derivative of x squared? So the 2 comes out, x to the first power. Now, I don't need to write the 1, right? Is that clear? All right, so I'm done with this piece, right? Done? Now I move to the next one. I have a plus, don't I? Plus. Now, 2 is a constant, but it's attached to a function. So the 2 comes for the ride. And then you look at the x. What's the derivative of x? 1. So that's just 2 times 1. And then I go to the last part. I have a minus. And then I have 7 by itself. What's the derivative of 7? 0. Y'all see how that works? And what do we get when we put all this together? We have negative 6x. And then what? Plus 2. Now, if you look back in your notes, didn't we get negative 6a plus 2? We got negative 6a plus 2. But now we're doing everything with x's instead of a's. Isn't that a lot faster than what you did by hand with the limit? Okay. So on your test, I'm going to give you a problem to do. I'm going to ask you to find the derivative, and I'm going to tell you to use the limit definition. And I'm going to want you to do that big, ugly thing. And then I'm going to say, now do it with the shortcut. And the good part about that is you should be able to check your answer, right? You should be able to know whether or not you got to the right answer. But I'll only ask you to do the limit one time, all right? Because this is a business calculus class, and we're not here to do limits. We're here to just get to where we need to get, right? We want to be able to apply this to some sort of business problem at some point. Okay, we good? All right, so in terms of the rules, that's it for now. Yes. Okay, so I do not have any other rules in this section. There are more rules that we need to learn, okay? But now, this is it. So it's time to do some examples, and then we're going to move into the next section where we're going to look at this thing called marginal analysis. Okay, so let's do this example here. How about this? Let's let f of x be equal to 5x to the negative 2 plus 1/3 x cubed plus 1. I would like for us to find dy dx. So what am I asking you to find? The derivative, right? So what is it then? Let's see. What rule can I use here? There's a couple, right? But overall, you're going to be able to split this into 3 different pieces, aren't you? You can do that because you have addition and addition. So there's 1, 2, 3 pieces to work with here. All right, so let's start with this first one right here. I'm just going to put equals, and let's call on some people. We haven't done that. We didn't do that last time. I think I'm just going to start picking names. Where's Quentin? Is Quentin here? Where? Quentin? All right, Quentin, I'm going to put you on the spot. So what about this right here? What should I do?
The 5 should be part of it.
So 5 is just going to come down? Okay. You're going to bring the negative 2 out. Okay, Quentin, be very careful here. Should have x, right? And now what power? Negative 3. Good, negative 3. So let's think about this. What Quentin did was he brought the negative 2 out, and then what he needed to do was take the negative 2 and subtract 1 from it, right? He needed to subtract 1 from this power. But negative 2 minus 1 is negative 3. So it's going to become negative 3 here. Is everyone clear on that? That's one place where students get hung up. And then, Quentin, I'm going to leave you alone. We're going to move to, where's Monica? Monica? Hey, Monica. How you doing today? Better? Okay. What do you think about the next piece, Monica?
You could ask me the other sides, then I would know. But
If I ask you what?
I said, you're going to ask me
This one right here?
Yeah.
Okay, well, what would you do with the 1/3?
Oh, it would just like go drop down.
It would come down, right? Because it's attached to the x cubed. All right, so it's going to come down. All right, now what about the x cubed? So what is the derivative of that?
Just multiply the fraction by 3.
Okay, good. So you're just going to bring the 3 out front, right? So just put the 3 here. And then you'll have x, and then what power, Monica?
To the second.
To the second power. So you're just subtracting 1 from 3. So you just get 2 up here. Good? Monica, you can finish it, I think, because the last part, what's the derivative of a constant by itself? 0. So you don't need to put plus 0 out here. I just want you to be clear on like where it's coming from. That good? Okay, now all we have to do is just kind of clean things up. So we've got to multiply these two together. That's negative 10. X to the negative 3. And then here, look, 1/3 times 3. Shouldn't these 3's cancel? And we just get the x squared. And then we don't need to write the 0 here. So we're done. Now I also want to point out that this is the same answer. Just remember, if you have a negative exponent, that you can drop it down and it becomes positive. So these are equivalent answers, aren't they? Okay. Okay, let's try another one. What do y'all think of these rules? It's good? A lot easier than having to do that limit, isn't it? Okay, next one. Let's use some different letters, okay? Because we've been using f of x, f of x, f of x. Let's do something like this. How about c of x, right? Cost function maybe, right? C of x is equal to negative 0.15 x to the 4th minus 0.25 x squared plus 1.75 x. All right, so we finally have some decimals in here, and we might need our calculators. All right, so let's go ahead and grab those, just so we can check ourselves to make sure that things work out correctly here. Okay, so how about Ebony? I thought I called on, did I call on you already?
No, I told you.
Okay. All right, Junior? Where's Junior? It's Junior, right? Not JR? I think he's sat there. He's not here right now. How about Michael Saunders? All right, Michael. How's it going, Michael?
Good.
Good? Are you understanding this so far? Okay. So, Michael, I'm going to let you start out. If I'm going to do the derivative here, what notation should I use here? Like, yeah, c prime of x. Good. So I'm going to write that. And then you want to go after this first one? Tell me what I need to do.
Drop down to negative 0.15.
Okay, so just bring that constant down. All right, and then
4x.
multiply that times 4, and then the x
3.
to the third power. Okay, good. That's it. Good, good. How about Matthew?
Matthew?
Matt or Matthew?
Matt.
Matt? Okay.
I want to see whichever.
Okay.
For the next one?
Yeah, you just walked in. Do you want to come back to you, or are you okay?
I think I got it.
Okay.
It would be, you'd subtract or minus 0.25, or yeah, 0.25,
Uh-huh.
2x to the first.
Okay, so I'm going to bring the 2 here, and that's multiplication between the 2, right? So I'm doing that times 2, and then x to the first power, which I'm not going to write the first power. Now, with this multiplication, I mean, you could put a dot here. If you wanted to, you could put like parentheses around those so you know you're going to multiply those. It's really whatever you want to use that helps you, that makes most sense to you. You just need to know that those numbers need to be multiplied together. Okay, and then how about Nathan? Where's Nathan? How about this last one, Nathan?
Will be 1.75.
1.75? Okay, times 1, which I'm not going to write. And then what goes right here?
You're adding.
Adding, right, so plus. Everyone good? Okay, so let's just multiply these. Do 4 times that. What do I get there? Negative 0.6, so negative 0.6 x to the third. And then when I multiply this, negative 0.5, 0.5 x, and then finally 1.75. So I'm not doing the derivative again. We already did the derivative.
So
Right.
If it does come out to 8 times 1, it doesn't need to be a constant.
Well, it is a constant, but we're not taking the derivative again. You only took the derivative from this line to this line, right?
Yeah.
So the constant came down, and the derivative of x was 1. So there's really like a times 1 here. And if I multiply those together, I get this.
Okay, that's what I was asking. So
Yeah.
making sure it wasn't-
Yeah, this is a 1 right here, not a 0. So, all right, what do you think? All right, let's do another one. All right, this one I'm going to call G of M. I'm just using different letters, okay? Is equal to square root of M minus cube root of M plus 6th root of M to the 5th. Okay. Now this is ugly, but I'm doing this because I want to make sure we all understand how to handle a root. So before I go about this, I just want to remind you how roots work, and I think I talked about this in the very beginning of class, that if you have the nth root of x to the mth power, that this is the same as x raised to the m over n. Do y'all remember me putting this up at some point? Okay. So anytime you have roots, you can convert them over to what we call rational exponents. And back in algebra, you're not real clear as to why you would ever want to do this. But now that we're actually doing calculus, this up here is a power, isn't it? And the power rule tells us that if we have x to a power, the power comes out and then we subtract 1, don't we? And you see how now it's more useful for us to write things like this than it is like this. So that's why we are got to be comfortable with that formula. So before we take the derivative, all right, before we take the derivative, let's just rewrite everything with rational exponents. And I think I'll cheat a little bit here to help. What's the number on the outside of this root? If it's not written, what is it? Out here is a 2 out here. And then right here there's a 1, isn't there? If it's just M? Okay. So, Lorenzo, no, I already called Lorenzo. How about Stephen Taylor? Is it Stephen? Oh, Stephen, I don't think he's here anymore. And Nicholas? And if I've called on you, let me know, okay? Nicholas, we're not taking the derivative right now, okay? I just want to rewrite all of these so that they look like this, all right? So what will that first one be, Nicholas?
It would be M
Uh-huh.
to, what is it? To the half?
Yes,
power.
to the half power, to the 1/2, okay?
That would be minus M to the 1/3 power?
Yep, M to the 1/3. You want to keep going?
Yeah.
Okay.
Plus M to the 5/6.
5/6. Good. Okay. So, I mean, the way you can kind of remember this is that this fraction right here, the numerator is always going to be the power that was already there, right? And then this is like the root. Don't roots kind of make things smaller? Like when you take the square root of 4, you get 2. So you can think of like the 6 is dividing and it makes things smaller. So whatever's out here is going to become the denominator of the fraction. However you want to do it, you need to kind of remember this though. All right? Now we are at a point where we can take a derivative. Because these are all, well, it's not x to a power, it's m to a power, but the rule still applies. So y'all ready for the derivative? G prime of m. Here we go. I'm at, is it Zara?
Yes.
Yes? Where are you at? Zara? Are you understanding this okay? Okay. Well, you've got kind of a messy situation here because of these fractions. So you get to try. So what do you think about this one, Zara? What do you want to do with that power? Because you have something to a power, right? So what have we been doing with the powers when we're taking derivatives? Move it to the front. Okay, so you're going to put a 1/2 out here. Is that all right? 1/2 like this. And then m. And then unfortunately for you, you now have to subtract 1, don't you? Okay, so I'm actually going to write that up here. I'm not going to do the subtraction yet. I'm just going to write 1/2 minus 1. Is that okay? We'll do the subtraction in a second. Zara, does that make sense?
Yeah.
Okay, Zara, I want you to do the next one then. So what would I write for the next one?
Would it be minus
Uh-huh.
1/3?
Uh-huh. And then m raised to the 1/3 minus 1. Yes. But don't say 1/3. Say 1/3. Be confident. Okay, you got it. All right. Math is usually like once you see it, it's I'm not going to say easy, but once you get what's going on, it's easy. Math is very difficult when you have no idea what you're doing, right? So if you feel like you've got it, be confident about it. All right. All right. Who wants the last one? Anyone want the last one? Go ahead. What do you got?
Plus 5, 6m
Plus 5, 6m.
raised to 5, 6 minus 1.
Raised to 5, 6 minus 1. Okay, so now we've got to go figure out what all of these are. We got to do 1/2 minus 1, 1/3 minus 1, and 5, 6 minus 1. And for that, I'm going to just do that on the side over here. And as we progress through this class, I may not show this step each time, but it's our first time. I want to make sure everyone's comfortable with this. If you're going to do 1/2 and subtract 1, you need to understand that that's the same as 1/2 minus 1/1. And what I'm doing is I'm setting myself up to get common denominator. So the common denominator here would be 2. So I need to multiply top and bottom by 2 here. So this is the same as 1/2 minus 2/2. And now that I have the same denominators, I can subtract these. And to do the subtraction, I take 1, I subtract 2, so 1 minus 2, and then I put that over the common denominator, which is 2. And so what do I get here? Negative 1/2, so negative 1/2. So this power is going to become negative 1/2. I have to do the same thing for the next one. 1/3 minus 1 is the same as 1/3 minus 1/1, which is the same as 1/3 minus what this time? 3/3 to get my common denominator. And then this is going to be 1 minus 3 over the common denominator. So this becomes negative 2/3. Negative 2/3. So this is just subtracting fractions. That's all this is. And the last one, 5 6 minus 1, I'll do it here. We have 5 6 minus 1 is the same as 5 6 minus 1/1, which is the same as 5 6 minus what? 6/6. So that gives you 5 minus 6/6, which is negative 1/6. So I'm ready to write my next line. So this is 1/2 m to the negative 1/2 minus 1/3 m to the negative 2/3 plus 5 6 m to the negative 1/6. That is your derivative. Yes, you could drop these down into the denominators and make them positive exponents, couldn't you? You could even do this. Watch this. 1 over 2 square roots of m. Okay, so look, m to the 1/2, if I drop it, m to the negative 1/2, if I drop it down, it's m to the positive 1/2, isn't it? And m to the positive 1/2 is the same as the square root. So isn't that what I would have? And then I could do that here also. Look, watch. Minus 1 over 3. And then what would I have down here? This right here moved down, so it's positive. So it would be what? What root? Is it a square root? No, because there's a 3 here. So it would be cube root of m squared. That's the same. And then the last one, the 5 stays up top. The 6 is on the bottom. This drops down and becomes which root? Sixth root of what? Just m. M to the first power, but you don't need to write it. So I'm just showing you that this is the same as this. These two mean the same thing. All right, that was kind of messy. All right, let's do another one. Let's go back to f of x. I hope that you've kind of caught on to the idea that everything we've done so far has pretty much relied on our ability to rewrite the problem as x to a power, right? And then bring the power out and subtract 1. Right now, the way this appears, you do have x to powers, don't you? Like this is x squared, this is really x to the 1/2, and this is really x to the first power, right? The problem is that they're in the denominator. And the power rule, right? The power rule says if you have x to the n, this implies that the x is on top. The rule itself implies that the x is up top. These are not up top. So is there any way that you could maybe rewrite this so that the x's are not down on the bottom? Could you bring this x squared up? How? You make it a negative exponent, right? So how about just rewriting? I'm not taking the derivative right now. This is the same as 4x to the negative 2. Isn't that? See, but I brought the x up, so now when I do the power rule, my n is negative 2, and that will come out. How about the next one? Minus 3. If I bring that root x up, what's it going to be? X to the negative 1/2. Good. Just remember, this down here was x to the 1/2. But then you brought it up, so it became negative 1/2. And then what about this last one? Plus 5, x to what power? Negative 1. And now you go through and do your derivative. So let's see here. I think we're at Caitlin. Where's Caitlin? No Caitlin? Georgette? Okay. Georgette, is this making sense to you so far?
Yeah.
Okay, what about this first one?
So you would bring down 4.
Okay, so 4 would be here.
And then multiply it by -2.
Negative 2.
And then x to the negative 3.
There you go. So you would, if we're going to write all the detail out, I would write 4 times -2 times x to the negative 3, right? But now that we've started to do this a little bit more, we're going to realize that when that -2 comes out front, we know it's going to multiply times that 4, right? So why don't I just do that right now and do the multiplication and just write -8? Is that okay? that coming out, that's negative 8, and then you said just x to the negative 3. Now, if you still want to write the intermediate step, that's fine. I'm going to go to that. Okay, any volunteers for the next one? Or I'll call on someone, but anyone want to volunteer for the next one? Go ahead. What do you got?
So you take the -1/2 times -3.
So negative 1/2 times negative 3, which would give you a what? Positive 1.5? Yes? So when you multiply 3 times 1/2, right? That's the same as 3 over 1 times 1/2. And just go straight across, 3, 2. So isn't that just 3 halves? Which is 1.5, but I'm going to leave it as a fraction. Is that fair? Can you do that? What's the power? This one's tricky. X to the, you're going to have to do negative 1/2, right? And you're going to have to subtract 1. I'm going to do that over here. You're taking negative 1/2 and you're subtracting 1. Which is the same as saying negative 1/2 minus 2 over 2, which is what? Negative 3 over 2. So you're doing negative 1, you're taking away 2. So I'm doing the same thing, common denominator, doing this minus this, so I get negative 3 over 2. Now you said negative 1.5, which is correct, but I'm going to leave everything as a fraction. So negative 3 halves there. Any questions on that one? Where's Jacob? Jacob? You already answered one, Jacob, so I'm pretty confident you're going to be able to get this. The last one?
It's going to be -5.
Negative 5, good. So the negative 1 times positive 5 gives you negative 5, and then x to what power? Negative 2, good. You're subtracting 1 from negative 1, you get negative 2. All right. We good? All right. I have 2 more examples and we're moving on. The next one is going to be a little tricky. F of x equals x cubed minus 4x squared plus 3x minus 1 over x. Does anybody have any idea how we can do this? How do you mean rewrite it?
All over X.
So you've got this over x, so what do you mean, what does that allow me to do?
All the x to the negative.
I agree with you, but I'm just asking you to try and like verbalize what you want me to do.
I don't know how to.
Okay. I'm willing to do what you want me to do, but you got to tell me what to do. Let me eliminate a few things first. One thing you might be thinking right now is, okay, look, these are all powers of x, and this is a power of x, right? So you might be thinking, I'm just going to do like, this becomes 3x squared. This becomes 8x minus 8x. This becomes just 3, and that becomes 0. So you just took the derivative of everything up top, right? And then you take the derivative of the bottom, which would be 1. That is completely incorrect. Unfortunately, when we have division like this, you cannot just do the top and bottom separately. That is a completely different rule that we haven't even talked about. We can only take derivatives of things that are split up by addition and subtraction. You cannot do a big old quotient. This is a quotient. You can't do a quotient the same way, just by picking off each piece. If we could, then this calculus would be a lot easier. But there's a rule, a new rule that we'll get like next class called the quotient rule that you're going to realize is a little messy. So, since we can't do that, we might still be able to somehow rewrite this as something plus something plus something or minus, somehow break it up. I think that's what you're suggesting, we break this up. How do you want me to break this up, though? I open this to anybody.
Multiply the denominator by the numerator.
Or bring the bottom to x and turn it to x to the power of -1 and distribute it through.
Oh, okay, so you could turn this in x to the 1, then bring it up, and then multiply it through?
Yes.
That would work algebraically.
Or you could just put x under each individual one.
Oh, so you could just put an x under here, an x under here, x under here, so like split it up? I think that's what you're getting at, right? Okay, so let's make sure we understand algebraically what's allowed and what's not allowed here, okay? Let me do this with an example. Let me show you something. What if I had, let's say, 1/3 minus 4/3 plus 7/3 minus 10/3? Could we put all these fractions together? Why? Because they all have the same denominator. And if I did that, then wouldn't I just take all the numerators and put them together and then put the whole thing over 3? Yes? So I would do like 3, and then I would do 1 minus 4 plus 7 minus 10. 1 minus 4 plus 7 minus 10, right? Isn't that what would happen? Okay, what we have here, this right here, is the same thing as what I have here. But we're starting with something like this. If you have multiple terms over a single denominator, you may split this up like this. So you can do the 1 over 3, the minus 4 over 3, the 7 over 3, and the negative 10 over 3 separately. That's what's being suggested. Now you would have the same result if you brought that up as a -1 and distributed through, but that's not usually the more common approach. So I'm going to split this up like this. Is everyone okay that this is like a legitimate algebraic move that I just made? Like that's fair? And now start to clean things up. X cubed over x is really what? X squared. So I'm getting x squared. Then I have minus, and then this is going to become what?
Minus
4x. And then here, look, those x's are gone. So plus 3. And then the last one, I don't want you to write that as minus 1 over x. I don't want the x down there. So what's it going to be?
Minus 1x to the -1.
Minus 1x to the -1. We don't have to write the 1 out here, but if you put it there, it's not wrong. Do y'all see that? Okay. Now, when you look at this expression, we have a bunch of pluses and minuses, and all the x's are raised to powers, aren't they? Okay, so we've gotten to where we want it, and now it's time to take the derivative. And for this one, I'm just going to take the derivative and see if you agree. Do all of these terms make sense to you? 2 came down, 2x. -4 came for the ride. What's the derivative of x? 1. So it's just -4. 3 by itself. What's the derivative of 3? 0. So it's not even here. This one, I had a minus. I'm bringing a -1 out. Negative and negative become positive, so plus. I subtract 1 from 1, and I get -2. So that's the whole thing. Okay, last one. How about x squared plus 1 to the 3rd power? So again, we run into an issue here. I mean, we do have x raised to a power. Like we could take derivative of this right here, right? We could take derivative of that. If that's all that was there, we would be done. But it's being cubed. And we don't have anything yet to deal with that. So,
I was going to say, wouldn't you
Yes, so the only way around this at this point, we will have a way to get around this shorter than what I'm about to show you. But our only choice here is to write it 3 times, because that's what it means to cube something, right? Right? Now, can we just take derivative of this, derivative of this, derivative of this? Unfortunately, no. See, because now aren't these products right here? Those are multiplications. We still don't have a rule on how to do multiplication, only addition and subtraction. The only multiplication we can handle is something like this. If it's a constant times something, the constant comes for the ride. But if we have 2 things being multiplied, like this, we don't have a way of doing that derivative yet. We will next class. We'll get what's called the product and the quotient rule. And then you'll understand why calculus starts to get a little messy once we start looking at those 2 rules. So we still can't do this. So what we're going to do is we're going to multiply all these together. It's going to suck, but it'll get rid of all the parentheses. So I'm going to start by doing just these 2 first. And I'm going to leave the x squared minus plus 1 out here. Okay, so what happens when I multiply these 2 together? I have to do a FOIL, right? Don't I? Like that? So what's that first multiplication get me? X to the 4th. And then we're going to do x squared times 1, which gives us x squared. Then 1 times x squared, which gives us another x squared. And then what's the last term we have? 1. Can we collect any like terms together? The x squareds, right? So we have x squared plus 1. Then we have x to the 4th plus 2x squared plus 1. Any questions there? Now, we have to do it again. We start with the x squared. It must multiply through to all 3. And then we do the 1 through to all 3. And we should have a total of 6 terms when we're done. So what is the first multiplication? X squared times x to the 4th. What is that? X to the 6th. Then x squared times 2x squared is going to be 2x to the 4th. And then x squared times 1, which is just x squared. So that's your x squared passed through to each of these. And now the 1 through to each one. So the 1 being distributed through just kind of gives you a duplicate copy of these 3 right there. Questions on that?
I have a question.
Yes.
So, like, just going back to regular algebra, when you have the 3 on the outside,
Yes.
can you just multiply it by the x squared plus 1 to the power of the...
You mean like cube this one and cube this one?
Yes.
No.
No?
I'll show you why in a second, but you can't. You're suggesting that we just we cube the x squared and we cube the 1. And that would be, this would be x to the 6th, and this would be just 1. That doesn't work. I'll show you why in a second, all right, after I finish this. I'm going to collect like terms. X to the 6th, let me see. How many x to the 4ths do I have? This one and this one, so how many of them?
That's
3 of them? 3x to the 4th. How many x squareds do I have? 1 and another 3, so 3x squared, and then finally I have a 1 at the end. So this is our function. And we can actually find the derivative of that now, can't we? So let me just write down right here what the derivative is. The derivative should be, you can do it with me, 6x to the 5th plus this one. 4 drops down, 4 times 3, 12. 12x to the 3rd. Good. Next one. 6, so plus 6x to what power? 1, and then finally 0. So that's it. This is our derivative. What do y'all think?